So today's lecture is about polarization. And polarization is a property of light that, when taken into consideration, can tell you more about your astronomical object than you would know if you were just taking into account just the brightness alone. So this, I think, is particularly useful in radio astronomy because we tend to deal with things more in terms of waves instead of, say, photons. And I think it makes it a little bit easier for us to kind of approach polarization as a concept, but also in terms of the way that we build our receivers. So polarization as an observational technique, it can be a little bit daunting. And so my goal in this lecture is to explain in very kind of easy to understand ways the properties of polarization, some stuff about electromagnetic waves, and hopefully you learn something interesting about polarization, and you want to use it in your observations because it really can give you a competitive edge in astronomy. So before really kicking off into polarization, I want to kind of do a brief recap of what is an electromagnetic wave. And the reason for this actually is I remember the first time I tried teaching about polarization, and I was, of course, went to the source of all knowledge, which is Wikipedia, and I'm reading this stuff about polarization, and it's always talking about electromagnetic waves. And I was thinking, like, hey, I don't really fully understand on like a deep personal level what is an EM wave. So I did a little bit of research and I got a better understanding of it, and it really helped me to understand the concept of polarization. So I just want to give a brief recap of EM waves before really kicking off into the polarization stuff. So bear with me if this is very simple stuff, but I want to start very basic and then build from there. So to make an electromagnetic wave, I want to just give a kind of physical, conceptual example. So let's imagine you have some kind of dipole, and connected to your dipole you have a oscillating source of voltage here. And if you apply a voltage to your anode and your cathode now, you're going to have one of your dipole halves having a positive charge and the other half having a negative charge. And, wrong way. What's going to happen is you're going to form a electric field. So the electric field will be pointing from the positive to the negative, as is convention. And this electric field, it will propagate from its source outwards with a propagation velocity of the speed of light, because it's a wave. And it's going to move away from where it was produced, right? It's going to propagate like a wave, and it's going to move away. Now let's say we then flip the voltage on our dipole, and we now have the charges arranging in the opposite direction as they were before. So now we've got the positive charges at the bottom and the negative charges at the top. So again, we're going to form a electric field, and now the electric field is going to be pointing upwards because it's going from the positive to the negative. So by this point, so some time has passed. Our initial electric wave that was pointing downwards has now moved onwards, outwards away from its origin, and now close to the origin we have a new electric field which is pointing in the opposite direction. So let's say we repeat this process and we keep oscillating our source of voltage, and now again we have the negative charges at the bottom, positive charges at the top, so we have our electric field pointing downwards. And each time we're doing this, some time is passing, so the electric fields that we were producing before have moved away at the speed of light. So what happens is, we keep repeating this process, and we produce what is an electromagnetic wave. So an electromagnetic wave is simply an oscillating electric field that is propagating at the speed of light away from our, in this case, away from our dipole. So in this case, our dipole is behaving like a transmitter. So this is what a simple transmitter is. You have two wires and a voltage across them, and you oscillate that voltage so that you make an oscillating electric field, and that propagates. And of course, the faster you make this oscillation, the higher frequency waves you will produce, and the more power you put into your transmitter, the more amplitude your waves will have. I want to now keep the same kind of concept in your mind, but just invert the situation. So let's say we have a pair of wires, so we have a dipole, and we have an EM wave that's coming in towards our dipole, propagating at the speed of light, and it reaches our dipole. And so we now know an EM wave is just a bunch of electric fields oriented up and down like this. And when this impacts on our dipole, now in the opposite to what we had previously, now it's the electric field that's going to be inducing a voltage, whereas before we had the voltage that was inducing the electric field, right? So the electric magnetic wave comes in and induces a voltage across our wires. So now, because the electric field is pointing downwards, we have the positive charges on the upper dipole and the negative charges on the lower dipole. And this essentially is what we have in a radio telescope. So I think some people might get angry at me for telling you that a radio telescope is just a pair of wires. You had a lecture, Antenna Basics, so Mitch gave Antenna Basics, I think, last Tuesday. So you will already appreciate that a radio telescope is a lot more complicated than just a pair of wires. But the kind of most fundamental component is these two crosshairs, which are receiving the electromagnetic wave. And I think it's quite important to know what is an electromagnetic wave before we really start talking about polarization. So I hope that was a decent recap of what an EM wave is. I think probably you all know this stuff already, but I just thought it would be important to just go over one more time. So now, let's talk about polarization. So I think we have now the vocabulary that we need to then discuss polarization. So the wave that we discussed a moment ago, this was oscillating in a kind of up and down direction, or we could say this is the vertical direction. And so the electromagnetic wave is made up of electric fields that are oscillating, and this is represented by let's say the y-axis here is the electric field's amplitude in the y direction. But you could also have an EM wave that has its oscillation in the horizontal direction, so moving kind of like this. And you could have a wave that's something in between, it's a bit like that. Or you could have a wave that's something different again. So I apologize for how messy these look, I had to draw them by hand. But the point being that you can have a wave that is composed of many different angles and amplitudes of oscillation. So what happens when you have, say, multiple components of EM waves traveling through the same part of space, the wave that you end up with is the kind of combined wave of all of the ones that you have. So if there's no dominance on, say, waves that are oscillating vertically or waves that are oscillating some diagonally or something like that, when there's no preferential order, this is when we say the wave is unpolarized. So if this wave were to be coming towards you, so just imagine, let's do like this. The wave is coming towards you like this, and instead of being vertically polarized or horizontally polarized or something in between, it's doing all of the directions with no particular preference, and it would look like this. So these arrows would represent the electric field directions of the incoming wave. Okay. So this would be the case for an unpolarized wave. Now you can have plane polarized waves. This is one kind of polarization. So in a plane polarized wave, you have oscillations that have one preferred direction. So in this picture here, this is, say, like vertical polarization. And again, I just want to use these little figures here. Imagine the wave is coming towards you, and in an unpolarized wave is going to be messy all like that, and the electric field can be in any particular direction with no preference. And in the case of plane polarized waves, is going to be only going in like one direction or one plane. So both directions of one plane. And with that, then you can imagine that there might not just be the vertical waves, but you can have other directions. So if we go back to our idea of this transmitter can only produce waves that will be oscillating in this case in the plane of the page. So we can imagine this is, say, like a vertical, so it would be doing like this. And one transmitter or one dipole can only really produce waves in one plane, like that. But we can rotate this transmitter such that we can produce waves that are now oscillating in the horizontal direction. So again, using this kind of visualization, if you imagine this wave is coming towards you and these arrows represent the electric field direction, now our transmitter, because we turned it by 90 degrees, is now producing waves that are oscillating in the horizontal direction. So in terms of linear polarization, and this is, we just mentioned a second ago, this is plane polarized waves. The two kind of main ways of describing these, that we're going to be using these terms a lot, so I want to introduce them, is vertical polarization and horizontal polarization. And sometimes people will call these like X and Y or V and H. It means the same thing, but the point is it's a linear polarization in one plane, and these two planes will have 90 degrees between each other. So they're orthogonal. And any kind of wave that you have then that is a combination of these, you can, let's say you have like a wave that is oscillating in a diagonal direction like this. You can work out what are the components of that wave, so how much that wave is oscillating in the vertical direction and how much it's oscillating in the horizontal direction. So you can decompose a wave into its y components and its x components. And the angle at which that wave is oscillating can be described or calculated in terms of its x and its y components. So you can calculate the position angle of this wave. So we've been using this visualization, right? So this is the field direction, the electric field direction of the wave coming towards you. Wait, my camera's opposite. Hold on, this is really hard. This way, okay? So the wave is coming towards you like this now, and we can work out this position angle by comparing the contributions or the amount the wave is oscillating in the x direction and the y direction, or the horizontal direction and the vertical direction. And we just take the arctan of that ratio to get the position angle. Okay, so I want you to take a minute to discuss between yourselves, just again to test your understanding, test your own understanding, test your colleagues' understanding, just to get these ideas fresh in your mind and also active in your mind. So the questions I want you to discuss with your colleagues for a minute or so is, what is an EM wave? And I left this picture up here for you to have some inspiration. Then what is unpolarized light? Waves, light, we'll be using those terms interchangeably. So what is an unpolarized wave or unpolarized light? Then what is vertical polarization and what is horizontal polarization? So take a minute or so, discuss with your colleagues, and the other instructors will be around if you want to discuss with them as well. So yeah, if someone could pause the video now and then unpause when you've had a satisfactory discussion. Okay, so assuming you've had a satisfactory discussion, I just want to go through a few of these questions and how I would answer these. So what is an EM wave? If you were to kind of break it down the way that we did, it's just an oscillating electric field that's propagating at the speed of light. And we exemplified this in this idea of the transmitter, which I think is a really nice model for getting your head into this. Then what is unpolarized light? So unpolarized light is just where you have your electric field doesn't have a particular preference in any direction. So it can be going, any direction it really wants, but it's not really conforming to, on average, any particular direction. So you have to consider that this is a time averaging thing. So at any one point, the electric field will be pointing in one particular direction, but over, averaging over the wave as it traverses through space or time, there's no particular preference overall. So when you have vertical polarization, this is where there is a preference, and that preference is where it is to oscillating in the vertical direction. And yeah, following from that, a horizontally polarized wave, or what is horizontal polarization, is when you have a wave that whose preferential or most dominant direction of oscillation is in the horizontal plane, or like if you want to say x and y, then vertical is y and horizontal is x. So I think those concepts, these are basic concepts which probably you already knew, but I thought they were just important to go over, because we'll be using this understanding as we go forward, and it'll be useful in other lectures as well. I should just point out before we go on, we're not really mentioning at all the magnetic field component of the electromagnetic wave, and this is really just because we're taking we're talking in terms of radio astronomy, where we're talking about dipole antennas and stuff like this. So I'm gonna neglect the magnetic field stuff because I just want you to kind of concentrate on the E part of the EM, the electric field. So in this example, the wave components are oscillating in X and Y direction, and as you can see in this image here, if we were to take I think you can see my cursor, if we can take the Y component and take the X component, and when we're comparing these, they're in phase, right? So you can see quite simply, like, this is half of a phase for the component in the y-axis, and this is half of a phase in the component in the x-axis, and they reach the nodes at the same time. So then you have your peak and your peak. This is like 3/4 way through a wave, and they're peaking at the same time, and then they resolve at the next node at the same time again. So these two waves are in phase. And I mentioned before, but I'll emphasize it again, any wave can be decomposed into an X component and a Y component. And similarly, if you were to take it the other way, say you have an X directed wave and a Y directed wave, your overall wave will be the combination of these two. So when you're adding two waves and they're in phase, your third wave will be, again, it'll look similar to this, it'll be a sine wave with some angle, position angle, depending on the dominance of the horizontal or the vertical wave components. So I want now to mess with this idea a little bit and consider when you have these two components, but there's a phase difference between them. So this is what gives rise to circular polarization. And this figure is, I think it's a brilliant figure to go through. And so that's what I want to do here now. So we mentioned that when you have two waves, like an x component and a y component, the overall wave will be the sum of those two waves. So if we were to go through this wave, through its propagation direction, and decide where is the sum, where is the electric field pointing, where's the sum of the electric field pointing at each point. So if we start, let's say we're starting here at we'll call this time 0, and we'll say propagation is going this way. So at time 0, the y component of the electric field, which is this blue line, is at full power, right? It's at its peak here. And the green component, which is the x component, is at 0. So our combined electric field direction, combining those two waves, you're combining nothing with something, so is clearly dominated by the something, right? Then what do we have? This is 1/2, so 90 degrees later, so half a pi later, right? That's 1 pi. That's half a pi. Okay, so quarter of a pi later, so 90 degrees later. Now the vertical component is contributing 0 to our overall wave, and the horizontal component is contributing, at its peak. So we can think of this as say 1 and 0. And so the contribution from vertical is 0, and the contribution from horizontal is 1. So now our combined wave is going to be pointing fully in the vertical direction, horizontal direction. So we start in the vertical direction. After 90 degrees, we're now at the horizontal direction. Then let's take it another 90 degrees. So now we're halfway through the original wave. Again, our horizontal component is gone to 0, and our vertical component now is peaking, but it's peaking in the negative direction, so the negative vertical direction. So our overall wave now is pointing in, so our overall electric field is pointing in the downward direction. And then we can go through this over and over and over again, but I think you'll get the kind of picture that the overall direction of the combined electric field is gradually twisting around like this. And the overall wave, although it has this vertical and horizontal components, it's the overall wave, so the combination of those two, when you have half of a pi phase difference, that should be, when you have a half pi wave difference, then you have a coiling electric field as it propagates in this propagation direction. So this is what we call circular polarization. And this is actually, I think this is quite a nice GIF that shows this. You have your electric field in the y direction and your electric field in the x direction, and then the combined field, which is represented here in black. And this arrow here represents the electric field direction. So we just went through step by step a second ago how this produces the coil, and I think this GIF shows it quite nicely. So you'll have, when we do these diagrams, you remember the unpolarized one kind of looked like this, and the vertical polarized one looked like a line like this, and the horizontal polarized one looked like this. So if the wave were coming towards you, the electric field would be going around in a circle, so we represent it with some kind of diagram like this. So yeah, I think this, if you want to discuss this in a bit more depth with the instructors, then maybe pause the video and have a bit of a chat. But if you're okay with this, which I think based on the background that we've already given, I think this is a not so crazy step to go to. I think you'd probably be okay now with the concept of circular polarization. Okay, so just like in the case that we had vertical polarization, and orthogonal to that we had horizontal polarization. In the case of circular, we can have left-hand circular polarization and right-hand circular polarization. So if you look closely at the green lines in the circular polarized light, you see that they're in opposite phases to each other. So in the one case, the electric field direction will lead around this way in the right-hand case, and in the left-hand case, it's going to lead around the other way. You're going to always have, orthogonal components when you have waves, because like the combined wave is always the combined of the orthogonal components. Okay. The thing I really just want to emphasize here is, you have the vertical and horizontal. Those are the kind of vocabulary you use when you're talking about linear polarization, and then left hand and right hand are the vocabulary you use when you're talking about circular polarization. So those are the most, let's go back here a second. These are the kind of most extreme cases. It's not very common really where you have like perfectly vertical polarization or perfectly left-hand circular polarization or something like that in an actual signal that you'd be receiving with a telescope or even producing with a transmitter. In reality, most light is going to be elliptically polarized. And elliptically polarized light is where you have contributions from linear polarization and circular polarization. So if you look here, we've already gone through this idea of linear polarization. We've already explained how circular polarization is can be decomposed into X and Y components with a phase difference. And then if you were to have a light or a wave that contained both linear and circular polarization, you would then have something elliptical like this. And for the majority of astronomical sources, the light that you receive will be elliptical. It'll very rarely be 100% linear or even 100% unpolarized. So elliptical is the most common. And the way that we describe these variety of wave types, so the variety of polarization properties you can have for a wave. So we discussed linear polarization, we discussed circular polarization, we discussed elliptical polarization, and we discussed unpolarized light. You can, any signal that you have, any light wave that you have, you can fully describe it, all of these components, using these 4 parameters. And I know they look kind of scary, but they're actually really elegant, and if we go through all of these one by one, I'm confident that you might even like them. Because they're very useful, and especially in radio astronomy, they're particularly easy to use, again, because in radio astronomy we're dealing with waves, and our receivers are linearly orientated, or in some cases you do have real circular shaped receivers, but typically they're linearly orientated receivers, dipoles. And again, you've already had antenna basics, so I'm sure you already know that. So let's go through each of these Stokes parameters. So the first Stokes parameter is the total intensity. So what we have here on the left is these 4 Stokes parameters. There's only 4. And in the kind of this column here, we have how to formulate the Stokes parameters in a vocabulary for linear polarization. So just in like linear speak. And then over here we have the same kind of maths, the same equivalent parameter, but described in terms of linear waves. And sometimes it's easier to think of the Stokes parameters with linear waves, sometimes in circular waves, and I'll go through these one by one, so don't worry. In the case of the total intensity, actually, it's pretty much easy to think about it in linears or in circulars. We mentioned before that any wave can be decomposed into its vertical and horizontal components, and so it kind of stands to reason then that the total intensity of a wave will be the sum of its components. So it'll be the amplitude in the horizontal polarization direction plus the component in the y direction, the amplitude of the wave in the y direction. So it's just adding up the components that you have. So adding this one and adding this one. And similarly, for circular speak, then you just have the right-hand polarization added to the left-hand polarization. So this gives your total intensity. And I would say probably the majority of radio astronomy people mostly care about things like the Stokes I parameter. So when you see like a moment zero map or something, or these kind of I don't really have one at hand, but it's the total intensity, the radio intensity of your astronomical object. So total intensity, I think this one pretty straightforward. So the second one we have is the linear polarization degree. So again, I'm thinking of the wave in terms of x and y components. If you were to have a wave that was totally polarized in the horizontal direction, then this value here, so let's speak in like ones and zeros in this case. All of your wave, so 1, is in the x direction. So this parameter here is going to be 1. And for this wave, there's no component in the y direction. So this is going to be 0. So in the case of horizontally linearly polarized light, you got 1 minus 0. So your Q parameter, your Stokes Q, is 1. Now, if I told you that my Q Stokes parameter is minus 1, so the way that we're going to have that is we have to have, and we're only speaking in ones and zeros in this case, it would require that this parameter here would be 0 and this to be 1. So that means we have no contribution or in the x direction, and all of our electric field oscillations are happening in the y direction. So that's this case here, right? Nothing in the x direction, everything in the y. So Q parameter of, so Stokes Q, this is the way we would normally say it. So if you say you have a Stokes Q of 1, that's a horizontally polarized wave, and a Stokes Q of minus 1 is going to be a vertically polarized wave. And then something in between will be something in between, yeah? Of course, like there's one case where the something in between is a bit messy, because let's say you have like a wave that's propagating in the 45-degree position angle. The contribution in the x direction and the contribution in the y direction will be the same. So your x minus y will be 0, right? And so you would say my linear polarization is 0. Even though your wave is plane polarized at 45 degrees. So we need another parameter, and that's where the Stokes U parameter comes in. So the Stokes U parameter tells you the position angle, or the the polarization angle. So if you think of again this kind of wave that's coming towards you with its x and y components, we can work out what is the position angle, and I think we already had this on a slide earlier, just by comparing the amount of wave that's in the x and y directions and taking the arctan of that, and that gives you the position angle. So now we can see that in the case where we have a 45 degree, even though our Q parameter is not giving us anything useful, we can now, we'll have something in the U parameter that's going to tell us about the polarization angle itself. So in this case, it's computed using the amplitude in xy direction and cos delta, where delta is the phase difference. So we talked about having these phase differences in the x direction wave and the y direction wave. So we just take the cos of the phase difference and the amplitudes, and this can be used to calculate the U parameter here. So these two are a bit easier to discuss in terms of linear polarization terms. but the same things can be computed using circular polarization terms. It's just I don't really want to talk about those math. But we could, I mean, or maybe the instructors can, and I can get out of that one. Okay, so the last parameter then is the circular polarization degree. So this, of course, is much easier to think about in terms of circular polarization terms, and is quite similar to talking about the Q Stokes parameter in terms of linears. So it just tells you, the Q Stokes parameter, if you remember, tells you how much horizontal and how much vertical wave you have, and what is the difference between them, and which one is the strongest, essentially. And in the case of the Stokes V parameter, you have the right-hand circular polarization and the left-hand circular polarization, and the parameter is determined by what is the difference between them. So in the case that you have all of your wave like 100% circularly right-hand polarized, then this is going to be 1 and this is going to be 0. So in the case of we call it RCP, right-hand circularly polarized. So a fully RCP wave will have a Stokes V of 1, and a fully left circularly polarized wave will give you a Stokes parameter of -1, right? Because this is 0 and this is 1, so you end up with -1. So I think you can appreciate now that if you have any wave, elliptically polarized wave, totally vertically polarized, some combination of something else or whatever, you can fully describe that wave and its state of polarization using just these 4 parameters. And even if you don't care about how polarized it is and all this kind of stuff, you still need the Stokes I to describe the total intensity of the wave. So you can run, but you can't hide. Stokes parameters will find you eventually. So you might as well make friends with them. Okay, so I want you to take another minute to discuss the topics this time. What is unpolarized light? What are the 2 linear polarization components? What is circular polarization? What is elliptical polarization? And what is the purpose of the Stokes parameters? So I don't want you to describe all of the the math and stuff of the Stokes parameters, but I want you to give your impression of what is the purpose of them. Why do we care about the Stokes parameters? What do we use them for? So yeah, if someone can pause the video for a bit and have you guys have a chat, and then come back. I won't go through the answers this time, so I'm going to leave the discussion up to the instructors. Okay. So, assuming that you've had a bit of a chat, and I'm pretty sure you would have been totally fine with the first 4. Just to make sure on the 5th one though, the answer really is the Stokes parameters. The purpose of them is just a vocabulary for describing the polarization properties of light, and that's it. You can use them in math, you can use them in machines and correlators and all this kind of stuff, but the purpose of them is to describe as completely as possible light and its polarization properties. Okay, so I want to go to I want to give you a feeling of I mentioned how you can't really escape from Stokes parameters. You can't really escape from polarization either, because it's everywhere in nature. And I want to give a few illustrative examples of this. And I remember when I was looking into this, it was really fascinating, and there's a load of weird stuff in nature that is involved with polarization, and in human history as well, actually. So one that you might know from, I'm wondering where you might know it from. I think if anyone's got polarized sunglasses or something, you might have seen this one. So whenever light reflects off something, typically there'll be a component of that light. So this is great. So you see here, this is this diagram we were using earlier, where there's no preferential direction of the electric field in the EM wave, and it's coming from the sun, hitting the surface of the ocean, and there will be a component of this wave that is absorbed as it impacts the surface, and there'll be a component of the wave that's not absorbed, and that is reflected. So in the case of sunlight bouncing off the ocean, the horizontally polarized light reflects and the vertically polarized light gets absorbed. So what you're seeing on a light reflection is a horizontally polarized light. And this is actually utilized by people doing fishing because they get these Polaroid glasses which has a filter on them, and the filter only lets through one particular direction of light. So if you have light that's bouncing off the surface, right? It's the sky reflecting off the surface. So this blue stuff on the left here, this is actually the reflection of the sky, right? You can see there's shadows and stuff. These are maybe trees in the background or whatever. But this is light from the sky that's bouncing off the surface. If you don't want that and you want to cut it out, then if you wear some sunglasses that have a Polaroid film that only lets through vertical light, and it cuts out the horizontally polarized light, you can cut this out. What you're left with is the light that's coming from under the surface of the water, and that's not light that's coming from the reflection on the surface. The light is coming from under the surface, so that's not polarized. So that light, the vertical component, the horizontally polarized component of that light can get through your Polaroid glasses, and so you can see it. So you can see the bottom of what's under the water, and you can selectively cut out the surface reflection. So this is used in fishing, probably in some other cases, but I think the most well-known one is like river fishing, sea fishing, stuff like that. I was flying to Ghana one of the last years of the DARA training, and I had Polaroid sunglasses on, and I looked out the window from the plane, and I took this picture from my seat, and there's some weird effect where I'm not going to pretend to understand this one, but maybe the different wavelengths of light are polarized differently or something. I'm not entirely sure, but one cool effect of polarization in nature is if you've got Polaroid glasses and you look at the sea from a plane, it's really pretty. It's really colorful. But I can't really speak much more about that one because I don't really know what's going on. I just thought it was really cool. So the other one that's kind of happening more often these days is you have like 3D movies, where the idea of 3D movies is you have this kind of stereo vision that gives you the illusion of depth from like the parallax between your left eye and your right eye. So this is achieved by having like two images on the screen. One of them is horizontally polarized, the other is vertically polarized, and that's represented by these colored lines here. And then one of your eyes can take in light from, say, in this case, the horizontally polarized light, and your other eye takes in the vertically polarized light. And this gives you this stereo kind of illusion of perspective, which is one of the ways of making 3D glasses. I think more recently they started using circular polarization, because I took some of the movie glasses home, and I tried doing some experiments with reflections and stuff. So I tried using them for like this kind of thing. It didn't work. So I think at least in some cinemas they use circularly polarized light. And if you can go to the cinema and get some 3D glasses, there are a lot of fun things you can do with them like this. So when I was looking at polarization, and apparently this beetle is one of the only animals that uses circularly polarized light. So if you look at this beetle with left-hand circularly polarized light, you see a lot of these kind of iridescent patches and things, which don't appear in the right-hand circularly polarized light. So maybe these beetles can also see in polarization, so that they can, see each other's polarized light. I'm not entirely sure. But in any case, these beetles, they use polarization in some way. And then the last two are actually related, so bees and Vikings. So I would usually ask the class to try and figure this one out. What's the relationship between bees and Vikings? And there's a picture here which is a big clue. And this is a recorded lecture, so I don't really have the chance to ask you. So I'm just going to have to tell you. But the relationship is the sky. So the sky is actually polarized. If you look at the sky with polarization sunglasses or whatever and tilt your head around, you see these the sky changes shade. So this is with polarization here on the left, and this is without. And bees use this for navigation. And so did Vikings. So the direction of polarization, because now you're all experts in polarization angle, the direction of the waves coming from the sky are polarized such that they align to the direction of the sun. So if the sun is, you can see this, right? You have the floor and you have the sun, let's say it's sunset. The light from the sky is going to be polarized in this direction. So if you were to look at this light with polarized glasses with a filter this way, you can block out some of the light from the sky. And the reason why this is useful for navigation is because if it was cloudy and you couldn't see the sun, so let's say the sun was blocked out, but you could see some sky, then if you had a way of seeing the polarization in the sky, you could work out where the sun would be, and then you can use that for navigation. And there are certain crystals, this is really cool, right? There are certain crystals that you can look through that work as natural polarizers. I can't remember what they're called. They're not. I don't think they're dichroics, but you can look this up if you want, if you're interested. Then the most weirdest thing is there's actually a protein in your eye that responds to polarization, and there's an effect called Herding's brush. And this is a feature of the human eye that can actually detect polarization. So you can actually train yourself to see polarization with your own eyes. And that sounds crazy. I promise you it's not. If you look it up, it's real. And I did it myself once because I didn't believe it, and it works. So if you can do this, and then maybe one day you decide, I don't want to be a radio astronomer, I want to be a Viking or a bee, you can then use this technique to navigate when you can't see the sun. So, I don't want to just teach you practical astronomy things, I also want to teach you some practical Viking advice. So that's something for you to think about. So to bring it back to polarization in astronomy, there are a lot of ways that we can use polarization in astronomy. So in the same way that we talked about how reflected light has polarization that we can cut out, alternatively, we can, if we want to look at reflected light, then we can select the reflected light. So let's say you're really interested in the surface reflections on water, rather than blocking them out with horizontally filtered polarizers, you would let them through using vertically filtered filters. Yeah. In the same way that if you wanted to look at reflections in space, you would choose polarizations that would allow you to receive light from reflected light. So in the case of this image here on the right, what this is actually is a protostar surrounded by a disk of dust. And the light from the protostar is really bright. typically, if you were to look at the Stokes eye image of this, so the total intensity image, it would be way, 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 way too bright for you to see any of this disk around it, because it would just outshine it. In the same way that you can't see the stars in the daytime, right? If the sun wasn't there, you'd see it. You'd see the stars. So if you wanted to block out the light from the sun, or the light from the star in this case, which is unpolarized, then you can choose to look only in polarized light. So then you only see reflections, okay? So in this case, what you're seeing is, this is light that's reflecting off dust around the protostar, and then after reflecting off the dust is coming towards you, and you can observe it by selecting to observe only in polarized light. So then we essentially make the sun or the protostar dark and concentrate or focus on the reflections. So then we can start to see these things. And this is how in some cases you can discover things like exoplanets or proto-exoplanets. But this is used a lot for studying disks in towards the more optical infrared regime in astronomy. I think probably, at least in radio astronomy, the most popular use for polarization would be studying magnetic fields. And this is a little bit similar to the idea of Polaroids and a little bit similar to reflections. But if you have a magnetic field, your molecules are going to align to that magnetic field. And when in a cloud of molecules, if there's no preferential alignment, so they're all pointing random directions, each molecule is going to produce one wave. And if there's no preferential direction in the ensemble of molecules, then there's going to be no preferential direction in the waves that come out of that gas. But if you can align all of those molecules in some way, and then each of them is producing a wave, those waves will then have some preferential polarization direction. So the way to align these molecules, of course, is magnetic fields. So if you have molecules that have a positive and a negative aspect to them, so polar molecules, then if you have a magnetic field, those molecules will align to the magnetic field and then emit in a preferential direction, which you can then observe. And the stronger the magnetic field is, the higher fraction of those molecules will be doing this, and so the stronger the polarization of that light is. And now we understand the Stokes parameters. So if we can measure the Stokes parameters of that light, we can measure how polarized that light is, and then we can determine from some math, which I don't want to go into, what is the magnetic field strength and what is the magnetic field direction. And here's an example here. So the white contours, this is the Stokes eye, so the total intensity map, and you can see that the radio emission is mostly brightest in the arms, and you can imagine that this is coming from radio emission from high mass stars and supernova remnants, and is not going to be coming much from thermal dust, probably more from high mass stars, I would imagine, and jets and stuff as well. And then these little white lines, for each point in this map, the authors have measured the polarization intensity and direction of the light and the radio waves, and then they represent that by these little lines. So the bigger these lines are, the stronger the magnetic field is, and the direction of the line represents the direction of the magnetic field. So you can see in these distant galaxies that these magnetic fields tend to coil around in the same kind of direction as the spiral arms. So this is really cool. You can see the magnetic field in an entire galaxy just by looking at the polarization. Then you all know the cosmic microwave background. So this is the emission from ages ago in the universe, and it's still everywhere in every direction. And this too has polarization in it. So you really cannot escape from polarization. More simply then, if you watched my lecture on masers can also be polarized. So these are, I think these are hydroxyl masers around a dying star. You can't see the star itself. I think it's this cross here, but you can see the masers, and the author has measured the direction and intensity of the magnetic fields, again represented by these lines, and you can see that there's like regions where the magnetic field is stronger, regions where it's weaker, and then this general kind of twisting motion or like circular motion of the magnetic field. So these are all uses for polarization. Magnetic fields also in things like blazars and quasars and things. Basically, like any kind of radio source, there's probably going to be some aspect or some component of polarization that you could use. And this is why I mentioned at the start that if you do this, you have a competitive edge in astronomy, because this, in some cases, is not so easy to do. Some people just don't really want to bother, but it's additional information, right? This is, you can see here that the magnetic field or the polarization provides really useful additional information that you can choose to use or not use. I'm just giving you the tools to use it should you wish. So probably the most common use of polarization for lazy people is the most common use is to not use it properly. But it is always used in a sense that when you're combining the signals, so we talked about the Stokes I parameter. If you want to have more sensitivity in your image, we have the radiometer equation here. So you can either increase your bandwidth or you increase your integration time. And if you can't make a wider bandwidth for whatever reason, because the horizontal and the vertical are orthogonal, when you add them together, they don't like cancel out. They actually add like independent signals which reduce the noise by adding them. The noise is not the same. So the noise of the X and the Y combined is less than the noise of the X and the Y independently. So by combining the polarizations of your data, so say you take data with horizontal and vertical polarized data, by combining the two polarizations, you double your bandwidth, and so that's going to increase the sensitivity or improve the sensitivity of your data that you're taking. So yeah, probably the most common use of polarization is to not use it properly, but to just combine the polarizations for bandwidth. But this makes sense, right? Okay, so I want you to take another minute to discuss what is elliptical polarization, and I leave these pictures up here for inspiration. When have you used or experienced polarization in real life? So this is just anecdotal in your case. Have you come across polarization? Do you love fishing or movies or something like this? Or maybe you used it in astronomy already, I'm not sure. So just have a chat. And then what are some uses of polarization in astronomy? And again, we've already done this one, but I want to kind of drive it home. What is the purpose of the Stokes parameters? So you don't need to describe them all to me, just generally, like, what is the purpose? What do we use them for? Okay, so if you can pause the video and have a bit of time, and then unpause when you're ready. Okay, so the last topic now is how we measure polarization in radio astronomy. And this is actually quite nice. So we're quite lucky in radio astronomy. Oh, hold on, let me just make this stand up. We're quite lucky in radio astronomy that we get a lot of this stuff for free just because of the way that we built the receivers. So I'm not going to repeat everything that Mitch said about the antenna basics and stuff. But the important thing to note is we measure orthogonal polarizations in our feed. So typically these will be horizontal and vertical, and we'll typically, not in all cases, but we might polarize these. So basically convert them from linearly polarized to left-hand and right-hand circularly polarized waves. The reasons for this generally are stuff to do with if you have two telescopes observing the same source, depending on where the telescopes are, the source position angle on the sky is going to be different. And so this is going to mess with, it's called the electric vector position angle, which we discussed actually. It's the U parameter here, the polarization angle. The polarization angle will be different depending on your position of your antenna, and that's just a pain to deal with. So if we deal with things in circular polarization, when we're doing interferometry particularly, it just makes life a little bit easier. So yeah, what we get out of our antenna system then is the total power in the left-hand circular polarization and the total power in the right-hand, and so we can get our Stokes parameter just by adding these up, right? So that's pretty straightforward. If we just take the L, we get just the L. If we just take the R, we get just the R. We can then correlate the L and the R signals, so combine them in different ways, such that we get, we can do this math already essentially like in part of the telescope, and then we get out the Q and U parameters from the signals themselves. Then the circular polarization parameter, which is the Stokes phi, we just get from subtracting R and the L from each other. So yeah, the situation in radio astronomy is quite nice that we get the Stokes parameters kind of on a silver platter, the Stokes parameters. Then we're going to make things a little bit more complicated and think about interferometers. So we just mentioned how we make the R and the LCP for one telescope. So imagine you have one telescope with the RCP and an LCP, and another telescope, which you know very well, also with the RCP and an LCP. So we say R1, L1, R2, L2. And we can correlate the R with the R, correlated is X here, and that gives you RR. And then L with the L, and that gives you LL. And then R and L, L and R, which gives you R and L, L and R. So this is what happens in a correlator. And someone else will be giving a lecture on interferometry and VLBI, so I'm not going to go into detail here. I just want to mention that the RR and the LL, we call these direct or parallel correlations. And they will typically be very strong because the signal coming from the object should look pretty similar for both telescopes. Otherwise, they're not looking at the same object. So the direct or parallel correlations should be quite strong. The RL and the LR, we call these cross polarizations or cross-hand correlations because it's correlating one with the opposite in the other. And if there's any real detected cross-hand correlation signal, they're usually pretty weak. I think this will probably be discussed in more in depth by somebody else. But the thing I really want to kind of get at is that the Stokes parameters in an interferometer can be calculated very easily in an ideal case. So what we get out of the correlator, these are called correlator responses. So you have like R, X, X, so you can put in like vertical, horizontal, or left and right, or whatever you want here. But these correlator outputs, so this is your correlator here. These correlator outputs can be used pretty much directly to estimate the Stokes parameters. So yeah, interferometers are actually really effective at measuring the polarization properties of a signal. The issue is that things are not always that nice. So I'm not going to go into polarization interferometry data reduction here. It's one of my favorite things, but it's really a whole topic in itself. Basically, this situation in these maths here is the ideal case. Things are a little bit messier in reality. But generally speaking, the correlator outputs we gets you most of the way to working out the Stokes parameters, which then tells you, the polarization properties of your wave in full. It's hard in VLBI. It's not so hard. So if you do this with like a single dish, you can get the Stokes I, Stokes Q, Stokes U, Stokes V pretty reliably for a single dish. It just becomes a bit more complicated when you're trying to do this in interferometry, especially if the telescopes are very far apart. Okay, that basically comes to the end of this lecture. So I want to summarize just everything we've done, just to basically just drill this into your mind, so that when you go for a break, you got this all kind of straightened out. So electromagnetic waves are an oscillating electric field that's propagating at the speed of light, right? And each wave can be decomposed into orthogonal components. So we can talk about them in X and Y, or R and L. Is different vocabulary for the same thing. The linear polarizations can be horizontal and vertical with some position angle, and when the two components are out of phase, so if your horizontal and your vertical components are out of phase by half a pi, it's a quarter of a pi. Is a quarter of a wave, yeah. Then you end up with circular polarization, and this is a special case of polarization. So then, the realistic case in astronomy is that your signal is going to be elliptically polarized. So that's when you have a mixture of linear polarization and circular polarization, and that can be a little bit confusing because you have linear, you have polarization angle, you have circular. Don't worry, because Stokes parameters come to the rescue. If you know the Stokes parameters, you can fully describe the polarization properties of a signal. And in radio telescopes, that's quite nice because the correlator gives us the Stokes parameters with a bit of mess, but most of the way there. Yeah, polarization. If that sounds appealing to you, that doesn't sound too daunting, that's it. It doesn't really get much more complicated than that conceptually. You can do crazy math if you want, but conceptually that's pretty much it. And it can be super useful in astronomy. So we gave some examples of like reflected light, magnetic field, stuff like this. If you have this in your tool belt as a radio astronomer, you will have a competitive edge, because it's just something that a lot of people don't really want to deal with. It really tells you additional information. I think it's kind of everyone's duty to use this, because it's in the data. It's information that's in the data, and if you're a good astronomer, you use everything you've got. So yeah, I hope you enjoyed this. I hope you learned something interesting. Hopefully I'll be around for a question and answer session on this. If not, yeah, the other instructors, I'm sure they're very versed in this, and they can answer your questions as well. Okay, so thanks for that, and have a nice break.